Data structures are a brand new topic. So we've looked at databases, which is all about, you know, the big picture on how to store data and how to create relationships and things, which is great. Data structures we're going to look into a bit more detail. We're now going to sort of, it's a bit like deep diving on databases. More specifically, what are the algorithms, the best ways of searching, sorting, and storing your information. So we've done databases. Data structures is our next topic. After this, we're going to look at some floating point binary, and then it's going to get really, really interesting with CPU architecture. Then we're going to look at translators and operating systems and programming paradigms, object-oriented programming and Prolog, and all sorts of other fun stuff. So still plenty of enjoyment yet to come. And today, we're going to look at these 4 things. Stacks and queues are very similar. Linked lists are totally different, and trees are just strange. But by the end of this, you will understand all 4. Yeah, and so, yeah, data structures, the data structures topic, there's actually 2 presentations on this. This one is about, these are 4 different ways of storing your data. And the other presentation, there's 2 different ways of searching the data and 2 different ways of sorting the data. So, yeah, this is what you can look forward to. So, first things first, the stack. So a stack is just a place where you can store your data, a way of storing data in a structured, ordered fashion. And imagine this sort of, you have an empty receptacle. This will probably be just a chunk of memory that you've reserved. We'll talk about static data structures in a minute, but this is a static data structure, which means you say, my stack is going to be 4 meg, and then 4 meg of memory is allocated, nothing else can use that memory space whilst the stack is using it. So it's there whether the stack is empty or full. So that's a static data structure, and that is your empty stack. You also have a stack pointer. When you create a stack, you also need a stack pointer in order to make use of it. The stack pointer basically says, well, you'll see what it does in a moment. So here's our empty data structure, and we want to put some data into it. So here's a chunk of data, and we're going to put it in, and as you can see, we now have an item of data in our data structure. And what happened to our stack pointer? It went up by 1. The stack pointer always points to the next free space. The next free space within your data structure. So if we get another piece of data coming along, what's going to happen to our stack pointer? It's going to go up by 1. Ta-da! And similarly, if we get another piece of data, then we lob that in, and the stack pointer goes up again. And what happens if a piece of data wants to leave our data structure? Data structure goes down by 1. So it does. So the stack is known as a last in, first out data structure. It is in bold and underlined because this is on the exam. A stack is a last in, first out data structure where you put things at the top and you take them out from the top. That's basically what it means. The last thing you put in is the first thing you take out. And you need to have a stack pointer. Yeah, and it's a very useful data structure for doing all sorts of different things. Yeah. I will put this presentation on Moodle. I'll put this podcast on Moodle as well. So if you need to go back and double check, then please do. So when you want to add something to this data structure, the first thing you have to do is check to see if it's full. If the stack's already full, then you can't add your data. But if it's not full, assuming that there is still space in your data structure, you add the pointer or add your data item to the pointer location, and then you increment your pointer, as we've already said. But you do need to know that it is on the mark scheme. And it's used when processing interrupts and using recursion, calling other procedures. We haven't really done processing interrupts yet, but you are familiar with calling procedures, aren't you? You have come across this before. So when you have, if you have like your lines of, oh, okay, interesting. I can't write on the board, it seems. Yeah, well, okay. So when you're going through your program, you're going through your program line by line, and you suddenly get to a line of code which calls a procedure somewhere, you have to, before you go off and you run this code in your procedure, you need to store the, all your local variables. You remember we talked about local and global variables in F452? So yeah, you're running your code, and you get to a bit where you have to then, you get to a line of code that calls a procedure. You store all your local variables on the stack, and then you go off and you run your extra procedure. If in running your extra procedure you then have to go off and store another and go to another procedure, you need to put all the local variables from that procedure you just called on the stack. Does that make sense? Ideally, I'd draw a diagram, but it seems the pens and smartboard don't work
Would it be in the same stack?
at the moment. Say again?
Would it be in the same stack?
Would it be in the same stack?
If you had to store the variables from...
Yes, yes, it would. Imagine for a moment that, so we're just running through the code, we're running our main method, and then we come across something that calls the main method, or another procedure called by the main method. So you put all your local variables from your main method onto the stack, and then you go off and then you run your new procedure that you've just called. But then when you're running your new procedure that you've just called, if you then find if you then call another procedure, then you have to then put all your new local variables onto the stack, and you run off and you run this third procedure that you've just run. Then what happens when you finished running this extra procedure, when you finish running the third procedure, when you reach the end, you then have to go back to where you came from. How do you know where to go back where you came from? You get the information back off the stack. Yeah? And then you finish running the second procedure, and then when you finish doing that, you then need to go back to your main method. How do you know how to go back to your main method? How do you know what the program counter was? How do you know what the contents of your addresses were, the contents of your registers were? You pull them off the stack. Yeah? Yeah, and we'll talk about this in more detail, because we're going to talk more about sort of interrupts later on when we talk about CPU architecture and registers and things.
What if, once you've got to like the second procedure, what if you then go straight back to the first one without stepping that down through them?
You won't. I mean, when you call a procedure, you usually finish that procedure before you go back to where you came from.
Okay. So what if you called the first one again?
Then you effectively have recursion, in which case this would still apply. Because then you've got a procedure that's effectively calling itself. Yes, I don't want to think about the logic of that, but yes, you've got a procedure which is inadvertently calling itself. So what we have here, this is a static data structure. When you create your stack, you declare your size. You declare the size when you create it, which is great because it's really easy to set up. It's just like declaring a variable or declaring an array of some kind. It's static, it's fixed, it's already set up, which is nice and simple and straightforward. The catch is that even when it's empty, it's still going to consume memory. The 4 meg of space that you've reserved in your memory is still reserved, even if you're not using it. So if you've got plenty of memory, that's not an issue. But if memory is limited, if you're talking about an embedded device, then that may not be great. Yeah. So that's what static. So stacks are almost always static. Stacks and queues are nearly always static. Linked lists and binary trees are usually dynamic, which means their size alters if there's the size is altered as required. So you never get it's never too big. You can always put more things into it. And if it's empty, then it doesn't take up any space. The catch is that it's complicated, so you need to have more processing. So it takes a bit longer. And probably easier to accidentally create bugs because it's not quite so straightforward. As we shall see. Any questions so far? All makes perfect sense. So a stack is just, it's a bit like, literally just like a pile of paper. So you put things on, and then the first thing you put on is the last thing that you take out. Or if I put that one there, and then I put something else there, and I put something else there, and then I need to get something out, then I take them out in the order, in the reverse of the order I put them in. Yeah? Cool. What happens if you try and add stuff to a stack which is full? There's a term that you've probably heard before. Say again?
Overflow.
Yes! You get a stack overflow. This is a term that you might have come across before on your blue screen of death. And it's also a really good programming website. There's a website called stackoverflow.com which is full of really useful programming tips. Stack overflow means you've got usually quite a complicated error in your code. Yeah. So if you try and put something into a stack which is full, or a buffer which is full, you get a buffer overflow. A stack overflow. Shouldn't have said buffer. I haven't got to that bit yet, but that's in the next few slides. So, queues. We've done stacks. That's basically any questions on stacks? It's pretty obvious, fairly self-explanatory. A queue is very similar. But a queue is not a first in, last out. A queue is first in, first out. And this is exactly like queuing for a bus, or queuing for your lunch, or queuing for any other queue that you would find anywhere, where the first person that arrives gets served first, and the last person to arrive gets served last. Where you put things at the top and take them out from the bottom. But this requires 2 pointers, where you have a head and a tail. How do they work? I'll show you in a moment. If you can bear the suspense. So yeah, with a queue, you put things at the top and you take them out from the bottom, or you put them in from the left and take them out from the right, or put them in the bottom and take them out from the top. Doesn't matter, so long as you're consistent. So long as the first thing you put in is the first thing you take out, then things are working well. So again, static data structure, and so you reserve your wad of memory, whatever it is, and even when your queue is empty, it's still taking up space. And when there's nothing in it, your tail pointer is the same as your head pointer. They're both pointing to 0, or the start location in memory. I suppose there's an outside, I mean, if this is your actual memory chip, then there might be sort of more, this might be straight in the middle, so this might be, I mean, I've put head pointer as 0, it might be memory location 4965 or something. But yeah, it's basically the first location in your queue. So, if we want to add something to it, what do you think is going to happen? That's what happens. Your head pointer stays where it is. Your tail pointer goes up by 1. Your tail pointer is now pointing to the next free location. So if we want to add something else, again, the tail pointer goes up, and the head pointer stays where it is. And if we want to add a third thing, same thing happens. So when you add stuff to the tail location. So what do you think the purpose of the head is? Yeah?
It's usually in the same sort of memory block. So like if you said like it could be right in the middle of the
Yes.
memory chip.
Oh, I see what you mean.
Going into the next like allocated memory.
Yes, kind of. You'll see though. So that's how we put things in. Every time you add something, you increment the tail pointer, and that's how it works. So what happens if you want to remove something from the queue? Yes. So if you want to remove something from the queue, that's the purpose of the head pointer. The tail pointer tells you where to add stuff. The head pointer tells you where to remove stuff. So if you want to take something out of your queue, you take it from the head. If you want to put something in, you put it in the tail. Does that make sense? Cool. So, yeah. And once again, the first thing you want to do if you want to add something is you check if it's full. And you add the item to the tail location. You add item to wherever the tail's pointing to, that's where you put it. And then you increment the tail. And if you're going to remove something, well, then you remove it from where the head is pointing to. And then you decrement the head. I say decrement, maybe I should also say increment. Although the examiners use the term decrement, so you might like to use it as well. Decrement means if increment means increase by 1, then decrement means reduce by 1. Though actually, as you can see from the diagram, you're actually increasing it in the same way you increase the head. So that's not entirely accurate. You increase the tail, and then you increase the head. Never mind. Sorry, did I just do that too fast? What I was saying was that, so when you add stuff, you increase the tail by 1. And then when you remove stuff, you also increase the head by 1. I know it says decrement. I said decrement because the examiner said decrement. So technically, you're actually incrementing the head still.
You have to say that you're decreasing it, even though you're increasing it.
Yes. Yes?
When it's empty, does it go back to 0?
Not necessarily. So if we keep taking, it's a good question. If we keep taking stuff out here, so if we now remove Elmo and then we remove Sunshine, what will what will the head be pointing to? Yes, and the tail will also be pointing to. Yes, so they won't be both pointing to 0, but they will be pointing to each other. So the way you know that your buffer is. Yes. And no, we shall see. I'm glad you're thinking about this way, because in a moment I will reveal the answer to your question. But for now, the way that you know that your queue is empty, how do you know your queue is empty? Because the tail and the head are the same. Good. That's not specifically on the mark scheme, but it's probably useful to know. If the tail and the head are the same, it means the queue is empty. And it's used in buffers. Can you give me an example? Where would you see a buffer? Yeah? On a printer? Yeah? The computer sends a bunch of data to the printer and then prints out the data in the order it arrives. I like to think of a keyboard. Keyboards also have buffers. I don't know if you've ever been typing away and your computer is sort of frozen and you haven't noticed and you keep on typing and you look up at your screen and, oh, I just typed things and they haven't appeared yet. And, oh wait, there they are. And they always appear in the order that you put them in. The first thing you put in is the first thing that gets displayed. The next thing you put in is the next thing that gets displayed. Yeah, so that's why they're used in buffers, because if you put them in a stack, then it will come out in the reverse order, which is not what you want. You would have to type everything backwards. You'd have to, oh, my computer's frozen. Never mind, I can get around this and type backwards. Which would probably confuse and enrage most people. So, there's our queue as it was before. What happens if we add another couple of elements? This is going to answer your question, Hamish. So, what happens if we add another couple of elements? What's going to happen to our tail pointer? What's our tail pointer going to be after I've added these two things? Say again? 5. Yeah, so the tail pointer is going to go up to 5, and the head pointer still stays as 1 because it's still where it was before. So, and now we're going to remove one more thing. So our head pointer is going to go up again by 1, you see? And we're going to add another thing to our queue. So what's our tail pointer? So our tail pointer was 5. We add one more thing. What's our tail pointer going to be now? 0? Wow, okay, clever. You skipped straight ahead. Okay, so one of two things will happen next. Either, when you try and add something new, it will simply say, the buffer is full. Buffer overflow is the error. Stack overflow or buffer overflow. Unless you have something called a circular queue. A circular queue is like a normal queue, but it basically wraps around to the way it was before. So if we want to add something now, where's it going to go? Now, if we want to add something to our queue, where do we put it?
The bottom by tail.
At the tail pointer. Again, you just add it to the location pointed to by the tail. And there it is. Have you ever played Snake? That amazing retro game where like your snake grows longer and longer and longer and the tail sort of follows you around. And if there's no walls, if it goes off the left side of the screen, it then appears again from the right side of the screen. A circular queue is similar, where basically this is the head of the snake, and then the tail of the snake is this way, and it just sort of follows itself. Just sort of wraps around. So that's what happens in a circular queue. Yes? Does that make sense? Good.
So how do you take the best bit out of the bottom?
Well, you have to wait until the head pointer is pointing to it. So now when you want to remove something, you can only remove stuff from the head. You can't remove stuff from anywhere else because you don't know whereabouts in memory it will be. When you want to remove something from your queue, you can only remove it from the head. So if you now want to remove sunshine, then you do, and then you increase your head pointer again. And similarly, if you want to remove woozle and heffalump and sandwich, every time you do, then they'll go up by one. The head pointer will go up by one. So that's it. That's queues and buffers. Any questions on them? Cool. Are you ready for... Actually, I think this might be a sensible place to pause and answer some questions on queues and linked lists, queues and buffers. So, if you have a look at the assignment, it contains a bunch of past paper questions. Some of them are about queues and buffers, queues and stacks, and buffers and stuff. So have a look and see how you get on.